Before we carry on building our shader, we need to say a little bit more about aliasing and how to correct it. In other words, anti-aliasing. If you'll recall, we are shading a micropolygon. A micropolygon has some area, some size. It's not just a single point. And aliasing arises when we try to give a color to the entire surface of the micropolygon, which just represents a single point sample of whatever procedural texture we're using. It's much easier to illustrate this in 2 dimensions. Let's imagine this sine wave represents a procedural texture that we're calculating and applying to our micropolygons. And the blue boxes at the bottom represent the micropolygons. If the micropolygons are small compared to the wavelength of the texture we're applying, the procedural texture we're applying, then we don't get much of a problem. The individual samples are sufficiently detailed to capture the color of the surface without too many problems. Our problem arises when our micropolygons become larger relative to the detail that we're trying to shade. So we can see now with large micropolygons, if we just take a single point sample per micropolygon, we're not going to get a very good impression of the detail of the sine wave. And this is made worse by the fact that if we're in an animated scene where the position of the camera is changing, or the position of the object is changing, then the dicing of the object may change from frame to frame, and thus the point samples can vary, and you may get flickering on the texture of your object. There are 3 different ways to tackle aliasing. The most accurate is to try to calculate the total amount of color or light for the area of your micropolygon, and then divide it by the area of the micropolygon to produce the average color for the micropolygon. And this is possible in some very basic cases, and indeed this is the technique we're going to use in the shader that we're constructing in this tutorial. But if you're using a complex procedural texture, it's very often not possible to accurately calculate the total amount of light. Another technique is to change the number of samples you take per micropolygon. And this is roughly equivalent to adjusting the shading quality that in Mantra itself, though it can be more efficient to do this within the shader. This technique is not very often used and is quite hard to program within your shader. A final technique is applicable when the detail of your shader is made up of features of different wavelengths or frequencies. So here we have an example where the top curve represents the procedural texture, and it's made up of 2 components. There's a low frequency component with a long wavelength, and then there's a higher frequency component. And this is actually quite commonly the situation with the noise functions that you find in Houdini, where you're layering noise of different frequency on top of each other. And what we can do in this case is, as the size of the micropolygons increases, we can fade out the high frequency noise and just leave the low frequency features to be sampled. And this too helps prevent aliasing. And in fact, this is the technique used in the shading node in Houdini, which is called anti-aliased noise. So let's build the next step in our shader. And I'm going to ignore the texture that we've laid down for the moment, and we're going to try and put a border around the object. And we're going to do this by creating a parameter which I'm going to call gap width. And if I type $OS in there, then the parameter name will be the same as the node name, and we can call it gap width, and it's going to be a float, and I'm going to give it a default of 0.1. And again, let's color this node. What I want to do is have a gap on either side of our object. So I need this to apply both when the S value is very low and when it's very high. An efficient way to do that is to remap our S value so that it varies between 0 and 0.5 instead of 0 and 1. And we want to remap it so that if the value is close to 0, it stays close to 0. It then rises to 0.5, and then as the value gets to 1, it decreases again to 0.5. And I can do this using an if statement. And I need a conditional, and I can get the conditional using compare. So let's feed our S value in to the first input of the compare. Hit P to bring up a parameter editor. I'm going to compare it to 0.5, and I'm going to set the condition to greater than 0.5, and I'm going to put this into the condition of my if statement, and then I'm going to feed the original S value into one of the inputs of the if statement. And if I go inside this node, we have an input and an output. And the nodes in between here will only be executed if the condition is true. And if the condition is true, S is greater than 0.5, so I want to subtract S from 0.5, from 1 rather. So we can do this using the complement node, which subtracts the 1 minus the input. So we feed S in, and we feed result back to S. Now, an if node works as follows. If the condition is true, then the code inside here will be executed, and the value of S that comes out will be different from the value that comes in. If the condition is false, then the value of S that comes in is simply copied to the output. So what we should have now is a value of S that varies between 0 and 0.5. And the next thing is to use a filter step. A filter step is a node which produces a value of 1 when the value you're testing is greater than the edge value, and when it's less than the edge value, it produces a value of 0. Now obviously the value we're going to test is the S that we've just changed, and the edge is going to be the width of our gap. So once we've got over the gap, this is going to produce a value of 1. And I'm just going to pause the video, and I'm going to duplicate that entire network for the T value. So I've now duplicated that for T, and the next thing we're going to do is mix two colors based on the output of these two filter steps. And for the filter steps, I want to get the minimum of both of them, which I can do using a minimum node, and I can feed the result of that into the bias of our mix, and I want one of these parameters to be a constant, and I want the other one to be a parameter. So let's have a look at the parameter first. I'm going to call this gap color, and it's going to be a color, and let's call it gap color, and we can set the default down here, and I'm going to make it a sort of dark grey colour. And then the second node, which is in fact a constant, I'm going to call white. And not surprisingly, we're going to make it a colour and set it to white. And again, let's colour this yellow. And finally, I'm going to take the output of the mixing of these two colours and put it into our output node. So now let's have another look and see what that looks like when it's rendered. So let's have a look and render this. And we can see we get a grey border around our grid. Now I've created two other parameters, width and height. Both are float values and they've got a default of 0.1. And we're going to use them to create multiple tiles. So I need a divide node, and I need to take the value of s, and I need to divide it by the width, and that's going to give me a value, since this is 0.1 by default, it's going to give me a value that varies between 0 and 10. But I need something going into these nodes here which value varies between 0 and 1. So what I need to do is take the fractional part of the result. So for example, this might give a result of 5.23. The frac node will produce a value here of 0.23, and I need to feed that into our compare node, and I need to feed it into the s on the if node. And I'm going to pause the video and repeat the same for t. So I've duplicated that for t. Let's have a look and see what we get when we render. And we now see we get a grid.